also wanted to take some time to thank the members of the CQR, Jason, Peter, Martin, and Chris. Definitely, you know what it takes to put together an event like this, to plan it and execute it, so it's definitely appreciated. The quality of the speakers, again, it has been excellent. Last year was my first trip at CQR, and the best word I can think of to describe my experience was inspirational. I was definitely inspired by getting to be in the room with people with such great accomplishments and work with them and collaborate with them. And this year, for sure, is no different. So what I tried to do was put together a view of repair data that can hopefully offer insights on how we can drive reliability and extend the life of legacy networks. And as Mike so astutely pointed out, that the legacy networks are a reality. They're going to be a reality for the next 5 or 10 years. So we have to deal with them. We have to understand what the risks are and how do we keep reliability high and drive improvement. So I have a data set here. This is a data set of repair transactions that we're performing in our shop in Tampa on a legacy platform, fairly high volume platform for us. This is an OEM program, so that means is that our customer is an OEM. We're doing it transparent, so the end customers would be all the major carriers. Unbeknownst to them, we're doing the repair on the backside. So this would be all the big telephone companies. So what I did was I looked at, this is actually a little over 11,000 repair transactions over the past 15 months or so. I parsed through all that raw data to kind of come up with patterns and trends and things that I can offer some advice on, or from some insight from a repair perspective, of how service providers can take reactive or proactive approaches, how OEMs can learn from the repair data and improve products going forward. So I broke it all down, and I came up with 5 kind of drivers to what sends units into repair. And no surprise that overwhelmingly aluminum electrolytic capacitors was driving legacy products. I have a couple slides on caps, so I'll leave that at that, and we'll go on to the next one. Physical damage and mechanical wear out. I kind of grouped these two together. They're very similar to me. What was surprising to me when I looked at the data is how many units that I saw that had broken PCBs, broken components, bent chassis, broken connectors, and things like that. And I think the lesson there is, from the service providers, a solid material handling policy, well-enforced policy, will for sure go a long way into reducing your overall repair spend. The mechanical components obviously are going to fail. We talked about drives earlier, fans, walk latches, not necessarily electrical mechanical, but simply mechanical components, and I have some examples of that as well. And then you have electrical overstress. This is lightning damage, power surges, transient voltages. There's not a lot you can do there. Mother Nature's going to do its thing, but there's some interesting points there I want to describe with the team. And then environmental conditions. So I grouped a lot of these together, but this would be primarily too hot ambient temperatures. I'll describe that. Also, dust, debris causing failure, and I can describe a little bit of that. And then last but not least, is insect infestation is actually a pretty big problem, especially with outside plant. So think about these insects. They're basically semiconductors, and they'll get in between And then no fault found. So no fault found is an issue. It's probably a contentious argument. It's a real problem with repair vendors. Anyone who's doing repair or testing in a lab environment, it's basically impossible to emulate all the different things that are happening in the real world in a lab environment. So there's always going to be some level of testing that can't happen. And I'll say that at the end. I think we have some discussion around that. So, on the capacitors. So, just as a review, high-value capacitors, primarily used in switching power supplies, power converters are what we're talking about here. The inherent flaw is there's a liquid component inside a sealed can. And over time, what happens is that liquid will leak out. And when it leaks out, it loses its capacitance value, and eventually the circuit will fail. Heat is definitely going to be an aggravator here. This says that every 10 degrees C rise in temperature halves the useful life of the capacitor. So capacitors are rated typically 25 to 30 years at 20 degrees Celsius. So if you go to 30 degrees Celsius, you took that to about 15 years. These systems are 30, 25, 30 years old. Modern capacitors definitely are better than the older ones, but they still have that same inherent design of a liquid core. So the problems can continue to persist. Some things we can do. So network operators for sure can visually inspect their equipment and detect problems before they fail. They take years to fail. So what you can do is you can check for discoloration. The picture here shows pretty bad discoloration. This was originally blue capacitors that are now black. Bulging. The capacitors will start to bulge as the pressure inside builds up. Also, you can smell. There's a pretty pungent foul odor associated with a bad capacitor. So operators can definitely inspect those, get those sent into repair to get the caps updated. OEMs. So I think the lesson here is don't underestimate how long these products are going to be in service and under what temperatures they're going to be exposed to. I'll describe that in a little bit more detail. So this is just a snip from a commercial component distributor that has a pretty good website with some pretty good parametric searches, and it's describing how capacitors are rated based on their endurance testing. So the one at the top is a Panasonic capacitor. It's $1.38 each by buy one, and it's rated for 2,000 hours at 85 degrees. Now 2,000 hours is not a long time. 85 degrees is extremely hot. It's not a real world simulation. It's just an endurance test that capacitors are put through when they're manufactured to give you a sense on how they're rated. The one at the bottom is a Nichicon cap. It's rated at 10,000 hours at 105 degrees C. Again, it's not a real world environment, but it tells you that it's a much higher durability capacitor. In this case, it's only 45 cents more per cap. In the manufacturing world, 45 cents, if you put 10 of those components on a board and you sell 100,000 boards over the life cycle of your product, it's $450,000. It's a huge component when you're talking about robots are doing the work. In a repair environment, 45 cents is nothing to the cost. Most of my cost is in engineering and in the labor of actually doing the work. So 45 cents will always use the more expensive and longer lasting components. And then this goes into a little bit more detail on how the caps are rated. I won't go into that. Physical damage, just some examples. Broken corners on the top right. This is clearly drops. We see it time and time again. Again, just going back to material handling policy. And then we talked about drives. This is actually a picture of a tape drive, that tape drive. And what happens is a rubber cap stand. It's made of rubber. It's about 30 years old. That rubber actually starts to decompose. It's not melted. It's actually just turning into tar, and that happens over time. And then the fans, same thing with the caps. With the fans, the bearings, you can buy bearings for 68 cents, or you can buy bearings for $68. Much higher quality, German-made bearings. So we always would put the higher quality components in for repair. And then, so electrical overstress. So what's interesting here, I've been in the business for almost 20 years. I know, you can't tell. I worked with many OEMs. I worked with Nortel, Lucid, NEC, Westcom, time and time again, and we all put the repair data into their engineering form so engineers can pore over it and figure out how to change design. And not one of them have ever asked us, when we have a blown component, did the fuses blow? And this is an example where clearly you have pretty bad power surge and perfectly good fuses. So there's just a design element that needs to be understood. Is the protection of the circuit working by looking at the repair data? So again, environmental factors. The picture on the right is a FLIR. This is a system operating in a perfectly 20 degrees C environment. And the ICs are rated to 140 degrees Fahrenheit, and they're operating at 133 in ambient conditions. If we're 5 degrees warmer or 10 degrees warmer, these ICs will be exceeding their thermal threshold and will probably fail. So it is critical to keep the equipment, especially legacy equipment, at a cool environment. Dust is another big problem. So when dust gets into a unit that needs airflow for cooling, the dust basically acts as an insulator to that airflow. The heat builds up. You can see some heat damage based on dust after we clean it up. So dust is a big problem with electronics. And I talked about insects. So I'll go back to NFF. So again, the problem with NFF is repair labs aren't able to properly implement all the environmental factors that go into it. Heat, for sure, is the #1 problem. Most repair vendors have some heat simulation to simulate hot conditions. The other end of that is cold. Not so many repair vendors simulate cold. It's much more expensive to simulate a cold condition as it is to simulate a hot condition. I can build a heat chamber with some of my maintenance crew. They can fit 2 7-foot racks for about $1,000. To do that, to get to 0 or -40 would probably cost $50,000 or $60,000. So definitely more economical to simulate heat than it is to simulate cold. The good news is heat is the primary factor for failure. Cold is not as much. The other things that have to be simulated is distance. Distance is a big one. It's hard to simulate distance in the lab. We use multiple techniques. We'll run cable back and forth across the building. We use resistors or LCR networks, but it's never as good as the real thing. And then real traffic is important as well. Oftentimes we're simulating traffic. Using real traffic will definitely flush out some failures. Having said all that, there's really nothing you can do to eliminate the problem completely. Every repair vendor that I'm aware of has a replacement policy or scrap policy for multiple offender no-fault valves, and simply because there is that gap of test coverage that cannot be overcome. But it becomes a question of economics, and the question is, how many units can I scrap before I spend engineering resources to solve the problem? I spent a couple of years of my life as a reliability engineer really on the front lines of dealing with this problem, where we bring it into our shop, we do all the testing, everything passes, send it back to the customer. He says, I plugged it in, as soon as I plugged it in, the unit failed, and we can't figure out what's going on. We send it back, our engineers scratch their heads for a few weeks trying to figure out how to make this thing fail, and to no avail. So the best solution is collaboration. Go out in the field, see what's going on, see what's happening, and almost always it's a fairly instant realization. We had one just a couple months ago. It's a motherboard. It's a computer motherboard that's actually using the cash register, and it's a newer program for us. But we got the test beds from the customer. We had a couple that were tested good. We repaired them, tested good. Customers said they failed right away. We couldn't figure it out. We had to burn it in. We did hot. We did cold. We did all the analysis. So we went to the site. They're actually local. Went to the site, and we saw the guy hook it up, and it's a cash register. So we had a keyboard that had a credit card slider in the keyboard. And he plugged that keyboard in, and as soon as he plugged the keyboard in, it failed. Well, we just had a regular old keyboard. We didn't realize that there's something with the keyboard. So instantly we realized what the problem was, and we were able to solve it. But boots on the ground, working with the customer, really is the best way to address that problem. The bullet point here, 93% of the no-fault valves that we sent did not bounce back. So the good news is, at least from a testing standpoint, we feel like we have a good amount of coverage. Now that 7% that did bounce back is definitely higher. It's actually 3 times higher than our normal bounce back. So it tells you that there is a gap in coverage there. But some of the problems, they could be happening. It could be software problems. or other non-hardware related problems. All right, thanks.